So now what we're going to do is we're going to talk about chemical reactions. And at the beginning of the year in chemistry, we talked about the difference between chemical and physical changes. Well, these are just chemical changes, and because a chemical change is taking place, we can go ahead and write some sort of chemical reaction for it. And a chemical reaction is just going to be when you have one substance that changes into another substance. The first thing to make note of, and maybe you even want to write this on your paper, is that whatever you start with, that is known as your reactant. So you start with one thing and you end with something else, which is known as your product. So reactants are what you start with, products are what you end with, and then in the process of going from one to the other, we symbolize it with an arrow, and we phrase that as being a yield sign. So reactants yield products. So in this little simplified recipe that we have here, we see we've got all these food groups here. What are the reactants? Well, it's the stuff you start with, such as milk, sugar, yeast, and flour, and then we end with the bread. So that's going to be the chemical reaction, and you're looking at the reactants and the products there. Okay, in a chemical reaction, it becomes really, really cumbersome for you to write out all of those words as to what you're starting and ending with. So as chemists, what we do is we use chemical equations and we use chemical formulas in there. This is nothing new. You guys aced this test. You did fabulous. When you were asked to write formulas for things, for nomenclature, you did wonderful on that. So all we're doing now is we're just adding in a little plus, a little arrow, but the rest of it is really just review. So if you were asked to write the formula for magnesium, what would you write? Mg. Oxygen, how do you write that? O2, so you have to remember your diatomics. That's the key here. And then finally, magnesium oxide. This looks like an ionic compound. How would you write that? It's Mg with what charge? +2. And oxide with what charge? -2. So that is it. It's just MgO. The temptation comes in from people looking at this and saying, well, it's going to form magnesium oxide, so I'm just going to take this and combine it with this. And they come over here and they write MgO2. Do not allow that temptation to get you, because what you have to do is you have to rethink it every single time, how you form those compounds. So that is review. We just threw in plus and an arrow in there. But now, according to the law of conservation of mass, which really just says you can't create or destroy anything, whatever you start with, you also have to end with it. So according to the law of conservation of mass, we need to fix this example. Here is our example, right down here, where we have magnesium plus oxygen yields magnesium oxide. The way we're going to fix it is by throwing in something known as coefficients. And these are just the big numbers right up front, in front of those elements or compounds that tell you how many of those elements or compounds you have. Notice that you can't change. I'm not going to be able to change or add subscripts to this. All I can do is add coefficients. So I would start with this and say, well, I've got 1 magnesium. Here's 1 magnesium, so that looks pretty good. Here, I've got 2 oxygen atoms, whereas over here, we only have 1. So what we need to do is throw in the big coefficient of 2. That's like the distributive property where it goes throughout. So you've now got 2 oxygen atoms in both sides, your reactants and products. But what did we mess up? Magnesium. So we have to put in a 2 here to fix the magnesium. Always go through a last step, and this one's pretty simple, but go through that last step of just double checking and counting. You've got 2 magnesiums, 2 magnesiums, 2 oxygens, 2 oxygens. So now it's balanced. We haven't created or destroyed anything. Did I? Okay. So one more that we're going to give a try to. Here, and also notice that this is a little bit more simplified than what you're going to see in your homework. You're asked to do some additional practice in your homework of writing those compounds. So for example, in your homework it might say something like phosphorus plus oxygen yields tetraphosphorus decoxide. And then you'd have to write all of that, plus then come back and balance it. So you have a little bit more work with your homework. But with this, it's pretty easy. 1 phosphorus, 4 phosphorus, so I put a 4 in there. Here I've got 10 oxygens, so if I put a 5 up front, I have 10 oxygens, and that's all you need to do. I'm not particular about putting a 1. It's more correct not to put a 1 in front. So when going through, it's okay. If you wanted to put a 1, I'd be fine with that, but eventually you're going to get to the point where you're not going to be doing it. So either way, it doesn't really matter. And then the key is, don't forget about diatomics. So when we look at these examples that you have down at the bottom of your paper, again, on your homework, it would say fluorine plus sulfur yields sulfur hexafluoride. So you would have to write those compounds. Here we've kind of written the skeleton for you, but you need to fix some things, and those things that you need to fix are going to be the diatomics. So in number 1, anything, is anything a diatomic? Which one? Fluorine. So fluorine needs to be 2. So what about sulfur? Nope, nope. Okay, number 2. Any diatomics? Oxygen. Well, if that's the case in number 2, then that would also be the case in number 3. I'll go through these kind of quickly. Number 4, which one? Cl, chlorine. Number 5, hydrogen. 6, oxygen. What about 7? Good, both of them. Nitrogen and hydrogen. Number 8, we just see oxygen, as well as number 9 and number 10. So all we've done now is we just went through and we made sure that all of those compounds and elements are written correctly by fixing those diatomics. On your homework, you have to go through writing those. So now that they're fixed, now we need to go through that balancing process. And to be honest, I don't like to spend too long on balancing. I know you guys have done this in the past. It's really, really important. So if you're not getting it, please come talk to me about it. But these that we have here for examples are not the tough ones. So we're going to kind of go through these quickly, and then at the end, I think I want to choose a few from your homework and pick out some of the tougher ones to go through. But on this one, or on this whole set, remember, I cannot change the subscripts. Those are written perfectly. All I can do is add in a coefficient. So I would start with this, and I'd say, well, I've got 2 fluorines. Here I've got 6 fluorines. So I'm just going to add a 3, and that fixes the fluorines. You've got 6 fluorines on each side. And what about the sulfurs? Anything? No, they're good. So everything is balanced. Number 2, I've got 1 zinc, 1 zinc. Here I've got 2 oxygens. Here I've got 1 oxygen. So what we do is we come over here and add a 2. That fixes the oxygens, but we messed up our zincs, so we have to add a 2 there. Number 3, bariums look good. When you start looking at those oxygens, this is where things get tricky sometimes. Here we've got 2 oxygens, but notice on the product side, on the right-hand side, you've got 2 places where you have oxygens. What I would key in on is the fact that you have an odd number. So if you fix that odd number, that can oftentimes help and make it an even. So this is the one I would look at, because that's what makes it odd. I've got 2 over on the right-hand side, but I've just got 1 right there, giving me a total of 3 on the right-hand side. So if I fix this and make it no longer odd, if I put a 2 there, and that gives me a total of how many on the right-hand side? 4. So you've got 4 on the right-hand side. Let's see if we can fix that on the left now. If I put a 2 here, that gives me 4, and miraculously it fixed our bariums also in the process. So that last step, 2 bariums, 4 oxygens, 2 plus 2 gives 4 oxygens. Okay, number 4, sodiums look good, chlorines are off. So I throw in a 2 here to fix my chlorine, which means I have to fix my sodium now. Okay, number 5, what catches my eye on number 5 is, and you'll see this lots of times when trying to balance, is you've got 2 and 3 for your hydrogens. So the easiest thing to think about here is finding your least common multiple, which is what? 6. So if I want to make 6 hydrogens, I need to put a 3 on this side and a 2 on this side. Well, that didn't quite fix it because now look at my phosphorus. So what do you think I have to do with these guys? Here. Double them. So this becomes, actually, let me start with this one because that's what we're trying to fix. So if I put this as a 4, if I double that, I also have to double this. Let's just double check and make sure we did that correctly. 4 phosphorus, 4 phosphorus. That's going to give us a total of 12 hydrogens, and 4 times 3 gives us 12 hydrogens. So that looks good. Okay, number 6. I'm going to put a 2 here for my lithiums. Then that throws off my lithium oxide. My oxygens are wrong, so I need to put a 2 here, which means, and it's okay, lots of times you'll have scratch outs or erasing, which means that this guy needs to go up to a 4. Okay, again, 2 and 3, so I'm going to do my least common multiple, and my nitrogens look good. Okay, next one where I have hydrogen peroxide breaks down to water plus oxygen. In this case, this is what catches my eye, the odd number of oxygen. So I think that's the easiest beginning point, starting point for this. If I make that even by starting with the lowest even number I can. So I put a 2 in there. So now I have a total of 4 oxygens on the right-hand side. So if I put a 2 here, I've got 4 oxygens on the left-hand side, which gives me 4 hydrogens and 4 hydrogens, so we're good. Okay, then we have potassium chlorate, breaks down to form potassium chloride plus oxygen. So I would look at this with my oxygens, same deal that we had with those hydrogens. What should I put here? 2, and here? 3? Okay, so now my oxygens look good. It's just the potassium and chlorines that are off. So what do we put here? 2. All right, and last step. Remember, it's okay to erase or mark through if you need to do that. But sometimes if you kind of catch the tricky parts, you don't even have to. I look at this and I see a 2 and a 3 for my oxygen. So I'm going to do a 2 here and a 3 here to get a common 6 on each side, which means 4 aluminums, and it's balanced. I went through that kind of quickly. Hopefully you guys feel good about that, but some of the others can be trickier, and that's really where I prefer to spend time. So now, what we want to do, now that we've got balancing tackled, we want to be able to identify different reaction types, and there are 5 main types of reactions, and you have this on the back of your paper. The first one we want to look at is something known as a synthesis reaction. What does it mean to synthesize something? To make or create something. So if you synthesize something, if you have a synthesis reaction, you're making something, and what we're making in this case is always one product. So that's how you're going to be able to identify these. So if you see one product, you know it's got to be a synthesis reaction. It's the only possibility. And the simplest type of synthesis reaction is when you have a single element and a single element that combine as reactants. The only possibility is that they combine. You can't do anything else with them. So these single elements combine to form one compound. That is going to be the simplest type of synthesis reaction that you have. If you look at your sheet, you also see on there that you have another example. On your sheet it says barium hydroxide plus water yields barium hydroxide. That's a situation where you have a compound plus a compound yields a bigger compound, so you're just mushing it all together. Eventually what we're going to do is we're going to predict these products. In fact, that day comes tomorrow. And we'll talk about how we can predict these products. You will not see this case tomorrow because this happens to be a special case, so you'll see that the following day. Okay, so those are our examples of synthesis. Here's another example. If you had something like sodium and chlorine, what's the only possibility? What does it form? Sodium chloride. So that's our salt. There we go. So that's a case where you have an element plus an element. and it forms sodium chloride. And remember, when you do get to the point where these are not written out for you and you have to predict the products, you have to think to yourself, how do you write sodium chloride? And you would say, well, sodium is a +1, chloride is a -1, so that's it. Then you would come back and you would balance it with a 2 in front of that. Okay. Synthesis is when you create one product. Well, the opposite of that would be when you start with one reactant, and that's going to be decomposition. So in this case, we have one reactant, which makes it really easy to identify. And all we're going to do is decompose it or break it down. I'm going to throw this your way, but don't worry about memorizing this or being tested on it. Lots of times with a decomposition reaction, over the yield sign, you will see something like heat written, or you might see a little triangle. That means that, hey, this, you know what, this is pretty much water, and it's going to stay water unless you give it a bunch of energy to have it decompose. So this is just a symbol saying that the reason it breaks down is because it was given some energy. So that's what that's about, but don't worry about that too much right now. Again, decomposition, you have one reactant that is breaking down into two individual elements, or a special case might be it breaking down into two compounds, and we'll see that in a couple days. So another example, aluminum oxide. What does aluminum oxide break down into? The only possibility would be aluminum plus oxygen. So here we go, aluminum plus oxygen. Okay, combustion. These are the easiest of all to predict the products of, because it is always, always, always the same exact products. You have carbon dioxide plus water. But what gets tricky with these is that they might be tricky to balance, and we can see why that is. If you guys remember from organic chemistry, you can get some pretty high coefficients, not coefficients, but subscripts in there. So high numbers, which means that those coefficients end up getting to be pretty high at times. But what a combustion reaction is when you have a hydrocarbon, in other words, hydrogen and carbon, might have other things in there, might have some oxygens in there, might be an alcohol, for example, but it's got hydrogens and carbons, it's in the presence of oxygen, it's given some energy, and it combusts. And every single time, whenever you have a combustion reaction, a hydrocarbon plus oxygen always yields carbon dioxide plus water. So those will always be the same products. So same products. And again, what gets tricky on these is that they might be tough to balance. And we see here are our products, carbon dioxide and water. Okay, single replacement is our fourth one that we're looking at. And this would be when you have the odd guy out that comes in and says, hey, I want to dance with her. So we have an element plus a compound, and you're going to get a new compound that's formed, and then a different element that is by itself. So there's going to be some sort of replacement, but it's a single replacement. If you look at the examples that you might have, remember the compound that's formed is going to be ionic. So that means you have a metal and a non-metal that are combined. And remember, you always do your positive first, then your negative, your non-metal. So in this case, if you had copper 2 chloride and magnesium is added to a solution of copper 2 chloride, so magnesium, when it forms an ion, it's positive, it's a metal. So magnesium, not that you have to worry about this for tonight's homework, but when we start predicting products, magnesium would replace the other metal, which is copper in this case. So if you have two metals, they would be the ones that might possibly be switching positions. The other example would be if you have this ionic compound and you have a non-metal that comes along, then those two, the two non-metals, might be the ones that switch positions. But there's a whole list of rules that we have to follow to see if this reaction will actually take place, and we'll see that tomorrow. So in this case, let's look at the next example. Here we have copper 2 nitrate. Add some iron in, and what we end up getting is iron 3 nitrate plus some copper that is left over. Okay, last one, and then we'll do some other examples. Last one is double replacement. And for these, what we end up seeing is that it's going to be when you have two ionic compounds, and ionic, positive, negative, music stops and they switch partners. So this positive is going to switch partner or switch positions with this positive. So in other words, A is going to now dance with D, and C is going to dance with B. So always remembering to put that positive first, that metal first. So in our first example that we have sodium chloride plus silver nitrate yields sodium nitrate plus silver chloride. And finally, let's see if we can do this one. Help me predict the products on this one. Don't worry about the coefficients that we've got. That's kind of confusing because you shouldn't worry about those until later after you have everything written correctly. If we have aluminum nitrate plus magnesium sulfate, aluminum is the metal, so when it switches position, aluminum is going to pair up with which ion? Sulfate. So it becomes aluminum sulfate. Aluminum, what's the charge of aluminum? +3. And sulfate, SO4, what's the charge? -2. So the only way to write aluminum sulfate is Al2SO4 3. And then the last compound that's formed, what would be the name of it? Magnesium nitrate. Okay, so we have magnesium with a +2, nitrate with a -1, so it becomes MgNO3 2. And then once you have those written correctly, that's when you can come in and worry about your coefficients. So we can say 1 aluminum, 2 aluminum. So I'm going to try by putting a 2 there. Now here is a hint for you. When you have a double replacement reaction like this, notice that my polyatomic ions are intact. I have nitrate, sulfate, nitrates, sulfates. I have them on each side. So instead of counting my individual atoms, it makes it so much easier to count those polyatomic ions, and I like easy if I can get away with it. So here I'm going to say, as far as my nitrates, how many nitrates do you think you have? 6. So you've got 2 times 3, that gives you 6 nitrates. So we come over here and we say, well, in order to get 6 nitrates, we've got to put a 3 in there. So now you've got 6 nitrates. So my aluminums and my nitrates look good. Magnesium, I've got 1 magnesium ion. Well, here now I have 3 magnesium ions. So I need to put a 3 here to fix that. And then finally, 3 sulfate ions, 3 sulfate ions. So everything is good. If we were to go back and count our individual atoms, for example, right here, everybody look at that. I don't know if you can see that from where you're at. How many oxygen atoms are there? I think I heard it. 18. So we've got 18 oxygen atoms right here. We could go through that process and then you'd see you have 12 here, so that'd give you a total of 30 oxygen atoms on that side. You should have a total of 30 on this side also. That becomes really challenging and cumbersome to go through it that way. So it's much easier to keep your polyatomic ions intact if you can. There's a couple other hints that we'll see as we go through some examples also. So I guess we should look at, this is what our products would look like. There's aluminum sulfate and magnesium nitrate. Okay, last little thing we want to do, and I really dislike this because this does not show us much, but what we want to do is we want to be able to identify the types of reactions that we had on the front side. And remember, those would be synthesis, decomposition, combustion, single replacement, and double replacement. You are encouraged to use those little abbreviations. If you glance at that, there are only 2 types of reactions that are even shown in this. Which 2 are they? Good. So synthesis and decomposition. These guys aren't even shown in these examples, which is too bad. So we'll find some from your homework to be able to do that. So first one, what type is it? Synthesis. And the way we know is there is only one product. So again, one product. What about number 3? Decomposition, because you only have one reactant. So this is so boring that I'm just going to go through and do this. There we go. And so what I want to do now, I'm going to choose a few examples from your homework. Okay, so we are going to do a couple of the homework problems that really weren't very well illustrated in the notes. And the first one we want to do is number 13. And the class has just said that, yes, this is a combustion reaction. So it's nice. They show you the formula for butane, even though you guys know what butane is. And it tells us butane plus oxygen. How do you write oxygen? O2. All right. Gives us our products, but we know that even if it didn't give us our products, it's always, always, always going to be the same, and that's going to be carbon dioxide plus water. As you guys go through writing these things, get into the habit of giving yourself some space in front of those compounds to be able to write your coefficients. So now that we know we have written our formulas correctly, I toss aside my formula writing pen and I pick up my magic coefficient writing pen. So the only thing I can do with this is add coefficients in. I cannot change subscripts. So the first way I would approach this, and I chose kind of a tough one because the combustions can get kind of tricky sometimes with the coefficients. I like to look at it in order. I like to work on my carbons, then my hydrogens, and then my oxygens, because I've got oxygens in a couple different places over there in the product side. So my carbons, I've got 4 carbons on the left-hand side, so I'm going to go ahead and throw in a 4 on the right-hand side. I have 10 hydrogens on the left-hand side, so here I've got 2, so what do I need to throw in? A 5. Okay, all's pretty good so far. Now the oxygens come about. This is always going to be the last place right here that I throw in a number for my oxygens. I look and I see, how many oxygens do you have there? 8. What about over here? 5. So you have a total of 13 oxygens in your products. 13, that's an odd number. What times 2 gives you 13? 6.5. Is it valid to do that? Nope, you can't do that. So what do you think? Everything's balanced though. So what do you think we have to do to those coefficients? Exactly, double them up. So don't forget to double up every single thing. So now this becomes 2, 13, 8, and 10. Then of course that last step would be to go back and double check, especially if this is a quiz or a test. You have 8 carbons, 8 carbons. You have 20 hydrogens. You have 20 hydrogens. You have 26 oxygens. Here you have 16 plus 10, so 26 oxygens. Those are really the tougher ones, but if you kind of follow a system, they're not too bad. Okay, let's do, let's see here. We'll do 2 more. Let's do number 11. What type is number 11? Double replacement. Okay, so it starts with chromium 3 nitrate. Chromium, I know it's Cr. It's chromium 3, so it's plus 3. Nitrate, how do you write that? NO3, what's the charge? Excellent. Nobody even looked at their sheets on that. That was good. So plus 3 minus 1, we know it's going to be that. There's our chromium 3 nitrate. Plus potassium sulfate is K with a plus 1. What's sulfate? With a minus 2. So plus 1 minus 2 becomes that. Now, I'm given my products. But I know this is a double replacement reaction, and all that's going to happen is that the ions are going to switch partners. So chromium is now going to dance with which ion? Sulfate. So it becomes chromium 3 sulfate. Chromium 3 is Cr with a plus 3. Sulfate, SO4 with a minus 2. You've already gone through that hard work and figured out the charges of everything. So plus 3 minus 2 means it will look like that. And then finally, the last thing, how would you, well, it's written on your paper. It's potassium nitrate. Make sure you do not make the mistake when you're predicting products of saying nitrate potassium. Doesn't make sense. So it's potassium nitrate plus 1 minus 1. So now that we know we have written these formulas correctly, now we toss aside our formula writing pen, pick up that magic coefficient writing pen. All I can do, I can't change subscripts, so don't scratch subscripts out and try and change those. I have 1 chromium, 2 chromium, so I'm going to try and put that in there. How many nitrates do you have on the left-hand side? More. Just nitrates. Excuse me, 6. So 6 nitrates, so I'm going to put a 6 in here, because what I did was I counted my NO3s, right? So I've got 3 times 2. I've got 6 of those NO3s with a minus 1 charge. So now I put a 6 over here to show that I've got 6 of those NO3s with a minus 1. So chromiums and nitrates look good. Potassiums, I've got 2 here. Ooh, I've got 6 here, so what should I put right here? 3. And then finally, what about my sulfates? They match up. They're looking good. So we could go back through, and I encourage you to do this. Go back through, double check, and count them. Again, if you counted individual atoms, it will all add up. But if you can keep your polyatomic ions intact, I encourage you to do so because it makes it so much easier. Also, let's say you got to the point to where you are trying to balance this and you're just about to scream and pull your hair out. Then there's a good chance that means that you wrote one of the formulas incorrectly, because that happens, that if you were to do this with nitrite instead of nitrate, there's a good chance you wouldn't be able to get it to balance. Sometimes you can, sometimes you can't. So don't let that be, that doesn't mean you necessarily got it right if it balances. But if you can't get it to balance, double check your formulas. Okay, one more I want to do because I want to show a little example. Let me see here. Let's try, we could try number 1, or let's try, let's go with number, sorry, let's go to number 30. Number 30. What type of reaction is that? Double replacement. So here it says nitric acid. Nitric acid. I chose this for a couple different reasons. One thing is that it has an acid in there, and I want to make sure you guys remember how to write those. So it's an acid, H, nitric. It doesn't say hydronitric, it just says, so it's nitrate, NO3 with a minus 1, so plus 1, minus 1, we're done. Plus potassium hydroxide, K with a plus 1, OH with a minus 1. That's pretty easy. I probably should have chosen a different one because this is going to be pretty straightforward. But in this case, it forms potassium nitrate, K with a plus 1, NO3 with a minus 1, and it forms water. Now, we all know that the way you write water is H2O. But when you have a double replacement reaction like this, it is so much easier for balancing if you keep your polyatomic ions intact. So notice the polyatomic ions that we have. We have nitrate and we have hydroxide. So if you were to, instead of writing it H2O, if you wrote it as hydrogen ions and hydroxide ions combined, then that makes it easier when it's time to balance. And the reason I said I probably shouldn't have chosen this one now is because everything's plus 1, minus 1. So I should be able to look at that and everything's going to be balanced because there's no change in charge. It's all plus 1, minus 1. But when you'd go through this, you would say 1 hydrogen ion, 1 hydrogen ion. Notice I'm just choosing that hydrogen ion. One nitrate ion, one nitrate ion, one potassium ion, one potassium ion, and then one hydroxide ion and one hydroxide ion. So I'm thinking about this being separate. It just makes it a lot easier, especially when you've got things that are different than just +1 or -1. So that is really it for our notes.